So this is the recording for the take-home exam. And here's the first problem. The data for the exponential population growth of a species of bacteria on Jupiter's moon Europa. And this is a fictional story, so I just made this one up. Anyway, bacteria are taking over the moon's ocean. And here you have the time in hours, and here you have the number of bacteria. You can easily see 2, 4, 8, 16, and so on. So it goes up exponentially. And what I put in bold here, the words graph, initial population, exponential, equation, and how good is the fit, and so on. This is the stuff that you actually have to record. And please, legible, respectively typed what you hand in. Notice that some of these answers I give away about 1 hour here, for example. So let me show you what to do. So graphing is actually really easy. Just highlight these data here, hit Control-C for copy, go over to Desmos, put it in here, and just hit Control-V for paste, and there it is. And remember that at times you want to look at this one here, share your graph, and copy this one down because you may need it for me. Need to send it for me. Okay, then it says in here, the initial the exponential growth should be of the form, this one here, so n times e to the kt. So I would actually have to type that into Desmos and let Desmos do the analysis. So my variables changed in Desmos, y1, x1, so I can't really use n and t. So y1 is proportional, not equal, but proportional to the initial population n times e to the, and the to the is the caret symbol on top of the 6, k times x1. Remember, I Desmos changed it to y1 and x1. And the r squared equals 1 means that the fit is perfect, and you can see that on the curve here as well. That makes sense. I should push this a little bit over. There we go. So r squared equals 1, and the fit is perfect here, which makes sense because I gave you perfect data. The initial population is 1, and the constant k is, which is the growth constant, 0.693. And I actually gave quite a bit of stuff away here for this one already. All right, problem 2, data for exponential decay of radioactive isotope. Again, I gave you perfect data. Again, the stuff that you actually have to fill out is in bold. Here are some hints, just like before. And then again, I already filled in some answers, so you kind of already know that, oh, it decays per poison emission into oxygen 18. But you still have to find out isotope, and I put a site here, website in the footnote, which is on Wikipedia, so that's where you have to look up certain things. Okay, again, you would take these data, then go to Desmos. So I just copied these data with Control-C and Control-V. There they paste. They don't, because I had the other scale here, they don't graph very well, so just hit that little plus sign right next to the table, and it should show up. There you go. I guess I didn't hit it right the first time. And this time around, it's a decay equation. I have a negative in the exponent as it goes down, which I can see from the graph. So I'm going to type that one in. I think, let's see, I have y1 and y and x1. So y1 proportional to, and what did I have for a variable here? An a. I did have an a. So a times e to the, again, it's the caret on top of the 6, and I don't have a lambda here, so I'm just going to use a k, but I have to remember that I need an x, I'm sorry, a negative there, times x1. There we go. And again, the fit is perfect because the data are perfect. Here's the initial activity, radioactive activity, 543 becquerel. And then the decay constant is 0.379. Actually, it's the negative in front of it because it decays. And then again, I actually gave a few answers away already. So this is the problem for rocket propulsion. Turns out that the velocity of a rocket depends on the mass ratio between the propellant and the payload, that means, for example, if you look at 30, that means that there's 30 times as much propellant mass-wise as there is payload. And then it turns out that the relationship doesn't go up nicely straight, but it goes up logarithmic. Of course, if you need a more powerful rocket, you would actually increase the propellant ratio to the payload. So the higher you get, the more velocity you get out of it. But it also turns out that as you get to, for example, from 20 to 25 versus from 25 to 30, yes, you're adding 5 more mass-wise propellant each time, but at the 30 here, it's harder to accelerate than it is at the 25 because you have more mass to accelerate. Hence, the velocity increase is not as much as it was before. So this actually peters out. It kind of goes less and less up. It's actually not asymptotically, but less and less. Okay, let's graph the data. So I'm going to take these here, and it's just, again, very easy in Desmos. Here they are. And then I'm going to put the equation in. We just saw it a moment ago, so again I have to use y1 is proportional to v times, so that would be the exhaust velocity of the propellant, times natural log ln, it recognizes that, of x1. x1 then would be the mass ratio, and I'm just going to put another term a in here, and I get a almost perfect regression coefficient, which means that my data are virtually perfect, which is true because I did make them almost perfect. You see, one of them is a little bit off, so maybe I did make them a little bit less perfect. And then we can see the 2,500 here, that would be the exhaust velocity, I think it was in meters per second. And then the negative 35 here is just to make sure that the curve works on this one here. Technically, it's actually gravity times the burn time, but I didn't put it in here, so don't put too much thought into the negative 35. All right, and then again, pay attention to these bold ones that you have to do, and there's a website that you might have to look up some of these. So this is the problem for trout being introduced into a pond. Notice that the pond has a limited size available to it. So as you give the trout time, months in this case, to reproduce and fill up the pond more and more, at some point it has to stop doing so. And you can see that in the numbers, they do go up nicely, steadily, almost exponentially actually. 14, 17 more, 21, 24, actually it is kind of exponentially. But then notice that they're going to slow down eventually, kind of around, let's see, here's 31, 27, 23, 20, 15, and so on. So they kind of top out because, yeah, the pond has only limited size, can only handle so many trout. So this is where the logistic equation comes in. And again, when you graph that in Desmos, it's really easy. So all I have to do is grab the data here. Remember that this is the logistic formula, and if I remember this right, I will actually try to plug it in exactly the way it is, almost exactly, with the ABC here, or CAB. So let's see. Here's my data. Oops, that didn't work. Why did that not work? I'll try that again. Oh, it's only because I grabbed one set of data. That makes sense. All right, so here's my table. There it is. And again, hit that little plus sign and try hitting it again. There we go. There's the, you kind of see here, it kind of goes off exponentially, but then it peaks out. So that's the logistic part of it. And then here I'm going to plug in y1 is proportional to, I want to just say c divided by 1 plus a times e to the negative b x1. The negative there is because at some point, if you do this exponentially, actually, then this here would go to infinity, which you divide by, which is fine, and then you get down to 0, but then you would lose all trout. So that's not the case. There has to be a negative here, which means this one here tends to 0, and it's just c divided by, which is the carrying capacity, actually the end population divided by 1 simply. And then you can see here, these are the parameters you come up with: 450, around at 9, around at 0.3, and that's what you would have to fill in here. And again, look at the ones in bold, what you have to do, and I gave some answers away. And of course, by me just graphing it, I also gave some answers away. This is the problem for the the luminosity of stars, really, depending on the mass of the star. So the more massive a star is, so for example, the one on top here is 20 times as massive as the sun. The sun is the gauge, being 1. The brighter it is. That kind of makes sense. It's able to burn more hydrogen, but it's disproportionately so. Notice that the star may have 29 times as mass, but it would be 214,000 times as bright, and that means that actually that's how much energy it sends out. How much more energy it sends out, which itself is logarithmic, as well, as we saw in a homework problem. So I take both logs of these here. I'm just going to show you when I actually graph these data here without taking a logarithm, I get this kind of curve. So here are these data, and here's my exponential on them. You can see that over here. And they, well, these are kind of like a little bit outliers and so on. And that, of course, is I use actual data, actually star data, so they're a little bit off. So it's actually a little bit easier to just graph them when you take the logarithm of both of them, and you kind of can see that here. The logarithm of 214,000, that's in the hundreds of thousands, so 10 to the 5th. Of course, logarithm looks for the exponent, so that's why you have 5.33, or 102,000 should be exactly 5, and there it is indeed. Or 955 should be really close to 10 to the 3rd, 1,000, and indeed it is. There was the almost 3, right? So instead, I'm going to graph these data here, these logarithm data. All right, so copy them. And let's see, there we go, and it's already adjusted. And at this point, it actually becomes a straight line relationship. So, and again, the data are not perfect because they're actual measurements. M times x1 plus b. B only has a meaning of being a factor in front of the mass ratio, but what's important is that the slope here is 3.4. The fit, by the way, is not as bad. I mean, it says 0.98 for the fit here, even though they do stray somewhat, but it's not too bad. And this here actually would be the actual exponent for the luminosity. And again, you would have to look at, in fact, that kind of give things away here. Notice the 3.4 right over here. And again, you have to look at what am I asking for the stuff in bold here.